This is an overview of how to derive the full Rydberg equation and then look at it mathematically in part 2, and then part 3 how to solve the Rydberg polynomial for all of the constants. There's 8 constants of physics that make it up. So anyways, here's part 1. I just do the old Howie Mandel. This is how we do free full Rydberg equation extraction, part 1. Basically, I just went through this equation for right out of the Wikipedia mainstream for the Rydberg constant for different nuclei, So anyways, I'm just dealing with the proton and single proton hydrogen. So basically, I say from that starting point, this equation, just rewrite it, rewrite this equation as, I just want to expand it into a simple polynomial in preparation for numerical method solution. So basically, just take their given equation, rewrite it. I'm trying to get 1 on one side. So you can see I just took and multiplied both sides by the denominator. So that denominator, you multiply both sides and bing, you get that. And then divide by Rm, so then I end up with 1 equals this ratio over the minus the mass of the electron to the mass of the nucleus, which for hydrogen is the mass of the proton. A single hydrogen. I use 0K because we don't want to have any photonic energy in there, because we're working to derive simply the constants of physics based upon the Schrodinger wave equation. That's where this stuff comes from. So anyways, you go up, as soon as you have this equation, the mainstream normally drops this term here, see if we can highlight it. However, we're going to use the derivation that I did in 1991 or whatever, and Feynman has a similar equation for the proton radius, proton mass. So anyways, you can develop the proton to electron mass ratio. Just use the inverse of that in this equation. And then from the mainstream, this R for very heavy nuclei is this, straight from the theory. Just plugging in the numbers right out of the Wikipedia. And you develop this Rydberg polynomial. This part right here is mainstream, and this is just adding the term they drop off. And they didn't have an equation for the proton mass, proton to electron mass ratio. The proton radius. So once you know what the proton radius is, in the equation for it, is plug it into the equation. So then, briefly of that, there's different ways to derive the proton to electron mass ratio. This is just one that I did a while ago, March 1st, 2016. The idea here is just, there's many different ways to do it. This is just one where you equate basically you take the Rydberg equation, just rewrite it, and it turns out this is like a momentum or a torque form, quantized angular momentum, quantized torque, I don't know what you want to call it. So it's written up for the electron, so I just did some mathematical assumptions or relationships and just said, well, if the electron's like that, let's assume a radius for the proton, put it there, and well, they got to be equal, because for every force, every action, there's equal and opposite one. Even with if it's spin or torque, there has to be an opposite one. So mathematically, it comes up with this correct ratio, correct answer for the proton radius. Just like Feynman, he derived it a different way, and there's different ways to do it too. You can do it from the Rydberg or the Schrödinger wave equation, like we did earlier in the blog. But I'm babbling on too much about that. So anyways, so once we have that equation showing the proton radius mass ratio, proton to electron derivation, we can jump to where we just evaluate these. So if the Google calculator is really cool, there's a link for it. A window right here shows it's the mass of the electron. Just put in the whole equation, elementary charge to the fourth. And all these terms are predefined constants in the Google calculator. And if you have your units all right, correct, it'll give you an answer. Usually if you have the units messed up anywhere, it won't give you an answer. So, and this is a pure number because the units all cancel out. So anyways, if you just take the raw equation, plug in what we know for the constants, well, holy baloney, it doesn't add up to 1. And that's due to the mainstream, the empirical, the measurement guys. They take the theory and drop that term and say, well, this is the equation we're working with. That has to equal 1 with all these constants in it. So they have 1, 2, 3, 4, 5, 6 constants, it looks like. They're all magically, when you put them in there, they equal 1 to, and this is how close to 1 it is, you know, almost 2 times 10 to the minus 10th. That's very close to 1, small error. And I'm pretty sure they tweak all these constants to make it balance with measurements so they get their 1. So anyways, once they bring in the proton radius solution and realize there's correlation or intercorrelation between all these constants, there's 8 of them in here now. 8 constants that you can solve for. So anyways, this is just looking at the numbers. We move on to the solution phase using numerical analysis. We're at 7 minutes and 30 seconds here. Using numerical analysis, this is the algorithm I did 81, 82, 83, I think it was 81, 82, University of Cincinnati, before I knew what the equation was, or equations like this. 2 summers or so, or a summer and fall quarter, developed on the IBM mainframe at campus with another guy or a couple other kids, young people. We were looking at solving different equations, polynomials for the roots. And so one of the things we developed was the sign flip algorithm, and that's what I used again to solve this in 91 or so. Blogging about it now, but so basically you do the basic program. We'll just do it. Just take a minute here. You open up this guy. You can go here and you download it. I'm not going to go through that, but then once you get over here, you just say load your program. I'm pretty sure it's, oh, don't need all my meme folder here. Let's go to my programs, downloads, documents. I wasn't going to go through all this basic program, and we'll just take 13 or 13.1. I'm talking on my computer right now. Repeat, and then you just hit run. So I loaded it up, hit the show output, and then just hit run, and it's going to run through. This is the error, so the error is approaching 0. It's using the sign flip algorithm to solve. It's not very many lines. It solves that equation for all of the constants that make it up, and that's why I want to use Excel, so I can plot the solutions and see if it's a stable, smooth solution or if it's jumping around. And make sure it's unique too, so there's more work to do, but I'm in about 10 minutes here. I'm going to just let it go until we see the end here. Yeah, So this window is nice and green. But here, when we go to it, we'll be able to scroll up and see the whole thing. I think for some reason it only does a little over 1,000 iterations. I improve the equation and algorithm to solve all 8 variables. So I'm only going to 14 decimal places. I need to get more decimal places. I mean, it's not practical, but I just want to see how far this will go. Because if it keeps on going more and more decimal places, and it's unique, it would be a way to show the solution is unique and stable. So still early here, early after 30 years. I'm going to let this keep on going. We're at almost 11 minutes in the video. And the good thing is it's almost done running, and I'm going to highlight the solution. Because I wrote it so that it prints out the constants instead of just barfing out the numbers like I originally did. It prints out the name and the values. And the units are MKS. I didn't bother to carry the units, but I work in standard MKS units. That's why everything balances out. So we're getting near the end, and this window just gives you the last 20 or so lines. With this one you can scroll up and down all the way to the beginning. Keeps on writing, wait till it's done, keeps on writing over it. It's getting close to, I think, 14 decimal places. We gotta get a little bit further to go. Oh boy, what? And it runs slow because this is on a tablet. It's an old Surface Pro 4, which they renamed. So on a cell phone, it runs way faster than this. This actually runs on a cell phone too. Earlier I blogged about how to write these loops too to solve polynomials for their roots. That's for, like, if you don't like solving things symbolically, you can always write algorithms for some sets of equations. It works. So we're getting closer and closer to 0. This is the error term. You know, because that whole polynomial is supposed to add up to 1, and I just subtract 1 from the answer, and it should be 0 when you get in there. Anyways, it's iterating, changing the values of all those constants by small amounts and checking the error, and whenever it's smaller, it keeps that setting and moves on to the other variable and decrements their. Anyways, I don't want to go into explaining the algorithm, but it's getting closer. 15 minutes. We're at 13 minutes. I bet you'll be done by 15 minutes. Got the doggies in the background. Stay here. 13 minutes and 40 seconds. Oh, we're getting close. I think it goes down 10 to minus 14th or so, and then it's done. There we go. And just the way it works too, for finer precision, I actually am decrementing it 10 minus 15th to 10 minus 16th, but just looking at the upper bits just for fineness. So anyways, there we go, it's done. So this, let me just show. So when it's done, it prints out, that's whenever the error is small enough, about 1 to minus 14th, so I call that 14 bits, or 14 digits of accuracy. So anyways, it'll print out the elementary charge. On the blog, I put the parentheses around. So I just copied and pasted the results. You can see it's still the last few digits are the same, and put the parentheses around after 14 digits, so those numerically aren't settled yet. So we're at 50 minutes and 20 seconds. You can see it just prints out the elementary charge. I had to fix that spelling error. Planck's constant, electron mass, proton radius, Rydberg constant, permittivity of free space, speed of light, fine structure constant. There's the final error, about 14 digits of resolution. Some other things, only 1,060 iterations. And one of the other things I'm doing is, it depends on how you look at this thing. If you're looking at, hey, this is a way to calculate pi, we got pi to, that's the ideal pi. We stopped where our pi isn't, I mean, we keep on fixing the digits of pi. Anyways, it's part of my check on the algorithm. Anyways, we're really good with our pi values, and the calculated pi value is good, if that's good. Anyways, we got the calculated proton mass. Here's where I have the fine structure constant, and it's different than the input. That's why I put those up here, 16 minutes and 30 seconds. Like the fine structure constant, I input this value, and it matches up to, on the 6th decimal place, there's a difference. And similarly, like on the proton mass, well, let me just double check. 3, 4, on the 5th decimal place, the fine structure constant's different. So their value is only good to 5 decimal places. On the proton mass, it's 6 decimal places a degree. They're off on the 7th. So that's it, 17 minutes and 17 seconds.